Welcome back to Manish Kumar channel. So today we are talking about the continuity, right? So definition, a function f where f is a complex valued function is said to be continuous at any point z0 if the following three conditions are met. First condition, limit z tends to z0, fz exists, right? Second condition, the function value at z0 exists. The third condition, the limit equals the function value, right? Here exactly z0 has been plugged, but here we are approaching towards z0, right? So left hand side and right hand side has that difference, okay? And both are equal and exist, then we can say that my function is continuous. In other words, you can say that for every epsilon greater than 0, there exists a delta greater than 0 such that modulus of fz minus fz naught is less than epsilon whenever z minus z naught is less than delta, right? So if you see a function of complex variable is considered to be continuous in any region R if it remains continuous at every point within the region R. So in the previous definition, we have talked about the continuity at a single point, right? But if your region R, your whatever the region is, this is your R region, and Z naught is single point, and if this Z naught can vary in this region wherever I want, right, in the entire region, and if the continuity definition holds true, then we can say that F is continuous on R. F is continuous on whole R, right? That's what the reason we are talking about. So because every point within R is continuous, so F is continuous on entire region R. Okay. And there are two results. If two functions are continuous at a given point, right, then both their sums and their products are also continuous at that same point, right? Their quotient is also continuous, right, at any such point, provided the denominator is not zero at that point, right? Otherwise, it will not make any sense. Another one important result, a composition of continuous functions is itself continuous. It means if you have a function f from this to this, right? F from your, you say, you know, xy plane, right, to uv plane. And then if you have another function, let's say z from this plane, uv plane to capital uv plane, then we can always find a composition function from this plane to this plane, right? Which is going to be z composition of f of z, which is going to be continuous. This is what this statement says. F is continuous at any point z naught, right? Then fz naught is defined here because of the fact that F is continuous means for every gamma fz minus fz naught, fz naught, fz minus fz naught, right, will be less than this gamma, right? Whenever z minus z naught is less than delta, right? And this gamma is for every gamma, this is going to be true for all gamma, right? Greater than 0, true. Okay. So now when you define function z, that will be the f z naught, right? Then at the same point z naught, when we are going to define a function, new function z from small uv plane to capital uv plane, then this will go to the same way, because if you see uh, z of fz minus z of f of z naught, right, absolute value, is less than epsilon whenever the same condition, whenever your fc minus fc naught, fz minus fz naught will be less than delta, right? So here delta will play a role of your gamma, right? And this is true for all gamma by default, so some gamma always exist, right? So therefore your function is going to be continuous. So this is your g composition f, is, you can say that, new function h, right? So that's what the composition of continuous function is, itself continuous. Okay, that's a very important result. Okay, another theorem, if a function fc is continuous and not equal to 0 at a point z naught, right? Then there exists a neighborhood or some neighborhood around z naught in which fz remains non-zero. So you can see very interesting result, and proof is very simple. Suppose that fc is indeed continuous and non-zero at that point, let's say z naught, right? So we can establish the theorem by choosing epsilon is equal to modulus of fc naught, since this value is not zero, right? Fc naught divided by 2, right? This implies there exists a positive number delta because of the fact that EF is continuous. So I'm choosing epsilon arbitrarily small enough, which is equal to Fc naught divided by 2, right? Then due to the continuity of the function, we can always find such epsilon, right? For every epsilon, we can always find a delta, right? Existence of delta is possible, such that fc minus fc naught is less than epsilon. This is basically epsilon, right? Fc minus fc naught is less than epsilon whenever z minus z naught is less than delta, because of the fact that this function is continuous. Therefore, if there exists a point c within the neighborhood of z minus z naught, which is less than delta, right? And we know if assume fc is going to be 0, right, in the neighborhood of that point, okay? So what had happened, if fc goes to 0, you plug 0 here. So what it results that modulus of fc naught only is strictly less than fc naught divided by 2. So what does it gives? It is not true, because any number is never less than by the number and it's divided by 2, right? So this provides a contradiction, right? You got me point on that. Why it's giving a contradiction? Because we are assuming that fz goes to 0, right? Then it leads to a contradiction. It means that fz should not be 0. And what is fz? Fz is the point around the neighborhood of z naught, right? Z naught is here, some delta distance is here, right? So z will be the point. It can be anywhere, inside or here, there, depending upon the distance of the delta, how you are going to manage, right? So in any neighborhood of z naught, some neighborhood of z naught, fz is not going to 0, because your function is continuous and not equal to 0 at this z naught. If fz naught is not equal to 0, then you can always find some neighborhood where fz never goes to 0. This is what the result says, right? Around the neighborhood, you will always find fz non-zero. This is a very interesting and important result. Okay, so another scenario, the continuity of a function fc equal to u plus iv, right, is closely, tied to continuity of its component function, right, u and v. Therefore, the function given in one is continuous at point z naught if and only if its component functions are continuous at that point. So f is continuous if and only if their components are continuous. That is very obvious, right? Another result, if a function f is continuous throughout a region R, and if my region R is closed and bounded, right, then there exists a non-negative real number m such that modulus of fz is less than or equal to m for all z is in R, right? And equality holds for at least one such z equality. So now what is the reason is, if you see fz is equal to 1 by z, and if I say my region R, let's say for example, if I'm doing R is not closed. So now let us say R is the region, right? R is the region. How do we define? This is strictly greater than 0 and less than or equal to 1. So how the region will looks like? Region will looks like this, right? So you can have a circle, right? And then you can have a circle, and then you can find this origin is removed, right? Origin is not there, origin is removed. Okay, so what had happened is, when I'm approaching, so this is not open, right? Not closed, not closed. This set is not closed because origin is removed, right? So this result required closed set, but I'm assuming that this set is not closed. So what had happened is, limit z tends to 0. What about the fz? Fz is undefined, right? You got it or not? So this reason, you see, if we remove the closeness condition, if we remove the closeness condition, your function is no longer even bounded, right? Or else if I say fc is equal to z only, right? And if I say your z is belonging to c, right? So z belonging to c means z can take infinity value as well. So this domain is not bounded. Whole complex plane is not bounded. You got important or not? If not bounded, if I take z tends to infinity, so this again gives infinity value. You got important or not? So if I remove boundedness condition, then I can find such functions which is not going to be bounded. If I remove closeness condition, then I can at least find some function which are not even bounded. So if I impose closed and bounded condition together of a continuous function, then that continuous function is always bounded. This is what this result says. You got a point or not? Okay, so this is a very interesting result. A continuous function defined and closed and bounded domain, right? Then the given function is always bounded. Okay, so problem we will discuss in the next lecture. Thank you very much. Please like and subscribe this video.